Context-free grammars can be badly designed. For example, they can have variables that play no role in the derivation of any terminal string and therefore shouldn't be there. That is analogous to states of a finite automaton that aren't reachable from the start state. There are also certain productions that, while they are necessary, cause derivations to take many steps that can obviously be combined. These include productions whose bodies are the empty string, or unit productions where the body is a single variable. We can get rid of these, and the way to do so is similar to the way we removed epsilon transitions from an NFA. Finally, we're going to introduce Chomsky normal form, where all the production bodies are either a single terminal or two variables. Incidentally, the Chomsky referred to is Noam Chomsky. Back in 1956, he wrote the paper that introduced the idea of context-free grammars. Then he was a linguist trying to provide some mathematics for the structure of the language. Since then, he has unfortunately become somewhat notorious for his political views. Oh well, back to context-free grammars. Here is an example of a really bad grammar. A is okay. It derives all strings of one or more A's using its two productions. However, B has only one production, and that production has B in its body. Thus, once a sentential form has a B in it, you can never get rid of that B, and as a result, B derives no terminal strings. To make matters worse, S has only one production, so that must be the first used in any derivation, but that production introduces a B into the sentential form, so it is impossible to derive any terminal string from S, and therefore the language of this grammar is empty. Almost all the algorithms we need to simplify grammars are based on the same principle, which I call discovery algorithms. These discover facts by an induction process. The basis is always certain facts that are obvious. Then, based on what is already known, we discover more facts in repeated rounds. Finally, at some round, they can discover no more facts. There's no point in going on, since without new facts at the current round, we cannot discover more on the next round. We generally have to prove only that any true fact of the type we are trying to discover will be found this way. Here's the image of discovery algorithms we should keep in mind. Okay, we start with some facts that you get from the basis. We expand the set of facts you know by using the basis facts. This is the first round. For the second round, we expand the set of known facts further by using both the basis facts and the facts you discovered at round 1. You keep going until at some round you have no more facts that can be discovered. So one of the first things we need to do when dealing with grammars is to detect and get rid of variables that can't derive any terminal string. We shall give a discovery algorithm to find inductively all variables that do derive at least one terminal string. Any variable not discovered by this algorithm derives no terminal strings and can be eliminated. For the basis, if a variable A has a production whose body has no variables, then A certainly derives a terminal string in one step. Note that this body could be the empty string. Technically, the empty string is a string of terminals. Now, suppose A has a production with a body alpha, and alpha consists only of terminals and variables that we have previously discovered to derive some terminal string. Then we can also conclude that A derives a terminal string. Since the number of variables is finite, eventually this algorithm terminates where it can find no more variables that derive terminal strings. It is easy to prove that whenever the algorithm says a variable derives a terminal string, that it really does derive a terminal string. We're not going to prove that. The harder part is showing that the algorithm doesn't miss anything. That is, if variable A derives some terminal string, then the algorithm will eventually discover A. We'll do that on the next slide. The proof is an induction on the minimum height of a parsed tree with root A and a yield of terminals. The basis is a tree of height 1, which consists of root A and one or more leaves labeled by terminals or perhaps epsilon. Then the basis step of the algorithm discovers A, so we're okay there. For the induction, assume the statement is true for height up to h-1. That is, all variables that are the roots of parsed trees with height up to h-1 and a yield of terminals are discovered by the algorithm. The parsed tree for A of height h, which must be, of course, equal to or greater than 2, has children of the root labeled x1 through xn. That's this. Any one of these xi's that is a variable is the root of a subtree of height at most h minus 1, and therefore it is discovered. Moreover, one of these variables is discovered last. At the round where the last of the variable ai's is discovered, we must surely do another round since the set of discovered variables just changed. On the next round, a will be discovered because it has a production, that is, a goes to x1 through xn, whose body consists only of terminals and discovered variables. The algorithm to eliminate variables that derive no terminal string is now simple. Use the algorithm we just described to find the variables that do derive terminal strings. Call the other variables useless. Then remove from the grammar all productions in which at least one useless variable appears. It doesn't matter whether the variable appears in the head, the body, or both. Here's an example grammar to which we first apply the algorithm to discover variables that derive terminal strings. For the basis step, we immediately discover A and C because they have productions with bodies that are terminals only. Here they are. For the first round of the induction, S is discovered because there is an S production with body C, and C was previously discovered. However, at the next round, we can discover no more variables. The only variable we have not yet found to derive a terminal string is B, and B has only one production body, which is little b, followed by big B. But this body does not consist only of terminals and discovered variables, so we can never add B to the set of discovered variables. Thus, B is useless, and we eliminate all traces of it. That includes not only the production B goes to BB, but the production S goes to AB, leaving us, of course, fortunately, S goes to C still remains, as well as the two A productions and the C production. In addition to eliminating variables that don't derive anything, we need to eliminate variables that derive some terminal strings but cannot be derived from the start symbol. The algorithm to find symbols, both terminals and variables, that appear in derivations from the start symbol is another example of a discovery algorithm. For the basis, obviously the start symbol can be derived in 0 steps from itself. For the induction, suppose that we have discovered that we can reach variable A. Then for every production with body alpha and head A, we can also reach all the symbols appearing in alpha, the terminals and variables that appear there. It is an easy pair of inductions to show, first, that if we discover a symbol by this algorithm, then it appears in a sentential form derivable from the start symbol. Second, that if we do not discover a symbol, then there is no derivation from the start symbol in which it appears. We're not going to give the proofs here. But remember, our goal is to get rid of symbols that do not appear in the derivations from S. So after discovering all the symbols that do appear in a derivation, delete from the grammar all the productions that contain a symbol in either the head or body or both that does not appear in a derivation. Say a symbol is useful if it appears in a derivation of a terminal string from the start symbol, and call it useless otherwise. There are two reasons a symbol could be useless. Either it derives no terminal string, or it appears in no derivation from the start symbol, or both. We have algorithms to eliminate symbols that are useless for each of these reasons, but we must apply them in the right order. First, eliminate the symbols that fail to derive a terminal string. And then eliminate symbols that do not appear in any derivation from the start symbol. In this example grammar, if, as we should, we first eliminate variables that do not derive a terminal string, we eliminate only B. However, eliminating productions with B gets rid of the only S production. We then use the algorithm to find symbols unreachable from the start symbol, and we find everything is unreachable. That is, all the productions are deleted. However, if we do things in the wrong order and first eliminate unreachable symbols, we find everything is reachable from S, so nothing is eliminated here. Then, when we look for the symbols that do not derive terminal strings, we eliminate only B. That leaves the productions A goes to C and C goes to little c, these guys, which should not be there because A, C, and little c are useless. Here's why first eliminating variables that don't derive terminal strings is the right thing to do. After eliminating those variables, every remaining symbol is either a terminal or it is a variable that derives a terminal string. After removing symbols not reachable from the start symbol, all remaining symbols appear in some derivation from the start symbol of some sentential form. But the variables that appear in sentential form still derive a terminal string because such a derivation can only involve symbols that are also reachable from the start symbol. Epsilon productions are those that have body epsilon. They can be eliminated from a context-free grammar, and the only thing that we lose is that we can no longer derive the empty string. If the empty string was not in the language to begin with, then we can eliminate epsilon productions and still have a grammar that derives the same language. However, if epsilon was in the language, then we lose it. The two cases can be summarized by the theorem on the slide. If L has a grammar, then L minus the set containing the empty string has a grammar with no epsilon productions. Notice that if epsilon was not an L, then L minus epsilon is just L anyway. To eliminate epsilon productions, we need yet another discovery algorithm, this one to find the variables that derive the empty string by one or more steps. We call them nullable symbols. The basis of the discovery algorithm is that if A has a production with an empty body, then it is surely nullable. And the induction is that if A has a production with body alpha, and alpha consists only of variables that are nullable, then A is also nullable. Here's an example grammar for which we will discover the nullable symbols. For the basis, we know A is nullable because of the production with epsilon body. It's that. In the first round of the induction, we find B is nullable because of the production B goes to A. That is, all symbols in the body, namely the A, are already known to be nullable. In the second round of the basis, we discover S is nullable because of its body AB, both symbols of which are already known to be nullable. This algorithm finds all and only the nullable symbols. We're not going to give the proof, which consists of two simple inductions. To eliminate epsilon productions from a grammar, we need to turn each production, say A goes to x1 through xn, into a possibly large number of productions. The idea is to guess which of the nullable symbols in the body of a production will derive epsilon in a particular derivation. Since we make all possible guesses by creating many different productions, we always manage to guess right. More precisely, for each set of nullable xi's, we delete these from the body of the production and make a new A production. Note that if two of the xi's are the same nullable symbol, then we have to consider the possibility that one position derives epsilon and the other does not. That is, we form one production for each set of positions that hold nullable symbols, not just for each set of nullable symbols. However, in the special case that all the xi's are nullable symbols, we do not consider the set of all positions, and we do not create a new production with the epsilon body. Here's an example grammar. Each of A, B, and C are nullable because they have epsilon productions. Okay. Thus, S is also nullable because of its production S goes to A, B, C. Let's construct the new grammar. For the S production, there are 7 subsets of nullable positions that we must use. The set of all 3 positions is also nullable, of course, but eliminating all of A, B, and C would leave an empty body which we don't allow. However, if we use the empty set of positions, we get body A, B, C. If we use the set of only the 3rd position, we get A, B, and so on. Now let's look at the A productions. We do not use A goes to epsilon, of course, but for production A goes to little a, big A, that's that. Only the 2nd position is nullable, so we get 2 productions, one with the variable A present and the other not. That's what we have here. The situation for B is the same. However, for C we cannot use the C goes to epsilon production. So in the new grammar, C has no production. That means that in the new grammar, although not in the old grammar, C is useless and must be eliminated. That forces us to eliminate all productions with C in the body, and we are done. The proof that the new grammar we construct generates the same strings except for epsilon as the old grammar generates is a little tricky, so we're going to give the details in one direction. As is often the case, we need to prove something more general than we really need. In this case, we need two statements about every variable A. First, if W is a non-empty string that is derived from A in the old grammar, then A also derives W in the newly constructed grammar. Second, if A derives W in the new grammar, then first of all W is not empty, and second, A derives W in the old grammar. Once we have that for all A, we can apply the statement to the start symbol and thus prove that the language of the new grammar is the language of the old grammar with epsilon removed if it was in that language. We're going to prove the first direction, and it is an induction on the number of steps by which A derives W in the old grammar. For the basis, if there's a one-step derivation of W from A, then A goes to W must be a production. We assume in part 1 that W is not empty, so A goes to W is a production of the new grammar. We make the desired conclusion that A derives W in the new grammar. Now let's do the induction. Assume the inductive hypothesis for derivations of fewer than k steps, and suppose W is derived from A in k steps of the old grammar. The first step of this derivation must be A replaced by the body of some A production. Assume this body consists of symbols x1 through xn. Then we can break W into W1 through Wn, where each Wi is the portion of W that either is xi, if xi is a terminal, or is derived by xi, if xi is a variable. All these derivations from variables are in fewer than k steps. If xi is a variable and the piece Wi is not empty, then the inductive hypothesis tells us that xi derives Wi in the new grammar. When we constructed the new grammar, we replaced the A production A goes to x1 through xn by a family of productions, and one of these eliminates from the body exactly those xi's such that Wi is epsilon. We know that is the case because if Wi is epsilon, then surely xi is nullable. We also know that not all Wi's are epsilon because W is not epsilon. That is, at least one xi is either a terminal or it is a variable that we do not need to remove from the body. Thus, in the new grammar, the first step can replace A by a body consisting of all those xi's such that Wi is not epsilon. We can continue the derivation in the new grammar by a derivation from each xi that remains of the non-empty string Wi. We know this derivation in the new grammar exists by the inductive hypothesis. We also need to show part 2. If W is derived from A in the new grammar, then it is non-empty and also derived in the old. We're going to skip this part. So we're now ready for a new simplification of grammars, the elimination of unit productions. A unit production is one whose body is a single variable. We can eliminate all such productions. The idea is to discover, using a discovery-type algorithm, all pairs of variables A, B, such that A derives B by a sequence of unit productions. Eventually, a sequence of unit productions must end with the use of some other kind of production. So we can collapse the steps that use unit productions into the next one that does not use a unit production. That is, if B goes to alpha is a non-unit production and A derives alpha by unit productions, then we'll add A goes to alpha. Finally, we drop all unit productions. At this point, we do not need the unit productions and can drop them from the grammar. Here's the algorithm to discover the pairs of variables A, B, such that A derives B by unit productions. For the basis, surely A derives A by unit productions only. This is a sequence of 0 steps. For the induction, suppose we already discovered that A derives B by unit productions. Then if B goes to C as a unit production, we may add the pair AC. There are 2 proofs that we need, but we're not going to do them here. First, an induction on the number of rounds of the discovery process lets us show that the pairs we find are valid. That is, they really are pairs AB such that A derives B by unit productions. And conversely, we can show by an induction on the number of steps of a derivation from A to B, using unit productions, that we will in fact discover the pair AB. Another proof that we're going to skip is the proof that a new grammar has the same language as the old. Again, we have to prove something more general, that A derives W in the new grammar if and only if it does so in the old grammar. Each production of the new grammar simulates one or more steps of a derivation of the old grammar. That is, some number of unit productions, perhaps 0, followed by a non-unit production. Conversely, every use of a production in the new grammar can be replaced by 0 or more unit productions followed by a non-unit production in the old grammar. We can now combine the 3 simplifications to make a strong statement about grammars. If L is a context-free language, then L minus epsilon has a grammar with no useless symbols, no epsilon productions, and no unit productions. Another way to put it is that L minus epsilon has a grammar in which every production body is either a single terminal or has length at least 2. We apply the constructions just learned, but we have to be careful about the order. We must start by eliminating epsilon productions. We have to do this step first because eliminating epsilon productions can produce unit productions that weren't there before, and as we saw in an example, it can create useless symbols that were not useless before. That could only occur if the production was only used to derive the empty string, however. Second, eliminate the unit productions. Third, eliminate variables that derive no terminal strings. We explained earlier why this step must precede the next step in our quest to eliminate all useless symbols. So finally, we do the 4th step of eliminating all the unreachable symbols. We've almost got our grammars into Chomsky normal form, or CNF. Such a grammar has only 2 kinds of production bodies, single terminals or 2 variables. We're now going to give the construction of a CNF grammar for L minus epsilon, where L is any context-free grammar. Incidentally, one important use of putting grammars in CNF is that it gives us a relatively efficient algorithm for testing membership of a string in a context-free language. One might imagine that it was easy to make such a test by looking at all derivations of a certain limited length, but with epsilon productions and unit productions in the grammar, it is not obvious how long the derivation of even a short string of terminals has to be. Moreover, even if we could bound the length of the derivation, as we can, we'd still be faced with an algorithm that took an amount of time that is exponential in the length of the terminal string. Rather, by putting the grammar in CNF, we can make this test in at most the cube of the length of the string. Our first step is to do the cleaning we just described. The result is the grammar no longer generates the empty string, even if the old one did, but otherwise the languages are the same. But all productions bodies are either a single terminal or have length at least 2. Our second step is to turn those bodies that are not a single terminal into bodies of all variables. The trick is simple. For each terminal a, create a new variable that we'll call a sub a. It's that. The job of this variable is just to generate the terminal a, so replace a in all bodies of length 2 or more by a sub a, and add the production a sub a goes to a. That is, of course, that. Here's an example involving the production a goes to b little c, b little e. C and E are terminals, so we must have created variables a sub c and a sub e with their productions. A sub c goes to c and a sub e goes to e. Then we can replace A goes to B, C, D, E by A goes to B, A sub C, D, A sub E. Now all production bodies that are not a single terminal are strings of two or more variables. If exactly two, that's great because that's what CNF requires. But if a body consists of three or more terminals, we have to break the body into pieces by using new variables that appear nowhere else. An example should make the idea clear. If we have a production A goes to B, C, D, E, then we need two new variables, say F and G, and they are used only for this production. They may not appear in the new grammar except as we describe here. In general, if the body consists of n variables, we need n minus 2 new variables. The job of the first new variable, F, is to generate the whole body, except for the first symbol, B in this case. That is, we replace this A production by A goes to BF. Now F needs to derive CDE, that's the rest of the body. But that's too long, so we use G to help. G derives only DE, that's this production, using the production G goes to DE, and the production for F becomes F goes to CG. Thus we've replaced A goes to BCDE by the three productions that meet the CNF requirement. A goes to BF, F goes to CG, and G goes to DE. These three productions can simulate the effect of the original production, although they take 3 steps to do so. Thus, making this change surely allows the new grammar to generate anything the old one did. But the new grammar doesn't generate anything the old one didn't, so their languages are the same. The reason is that once we choose to replace A by BF, we are forced to replace F by CG and then G by DE because these two variables have only one production. Thus, using A goes to BF in the new grammar is tantamount to using A goes to BCDE in the old. We thus have an argument why the transformations from clean grammars to CNF grammars do not change the language. You can do formal inductions on the length of derivations in these grammars, but I hope these less formal arguments are convincing.